Okay. Um, for the left side, this is a boost converter. Okay, because this is the current source, and then we have a voltage source, and then this is a buck converter, because we have the voltage source and then the current source. Okay, and we just make this. We just upside down this converter. Okay, then we have this one, right? Only upside down for the right side of the converter, and then we just how to say we have to let me do a little thing about this. What I want to do is here we just interchange the position of these two components. Okay, so we have the converter looks like this. We have a current source, and then we have the switch here, and we have a voltage source, and then we have the switch. Okay, and for the right side converter, we do the same thing. We just interchange the position of these two components. So we have the voltage source here, and we have the switch here, and yeah, the same for the other part. Okay, and then because we have the voltage source here and the switch here, so we just combine the two voltage source into one. Then we have the converter look like this. Is it okay for you? Because they have the same voltage source, so we just combine the voltage source. But we left the switches alone. We just let them untapped. Okay, then of course there are redundancy of the switches, so we eliminate one of them. Okay, so we take out. Okay, we cancel this one and also cancel this one. Then, we need only one active switch, and the other one can be replaced by diode. So for the left side, this is the active switch, and this is a diode. Then we have the converter look like this, and the voltage source is replaced by the capacitor, while the source part, the current source is replaced by the inductor and the voltage source. And the load, for the load side, the current source is replaced by the inductor and the load. Okay, this is a converter. This is sometimes called boost buck converter, but more formally, it is called choke converter. Okay, so choke converter basically is synthesized by boost and buck converter. So we expect the choke converter will also have the properties of buck boost converter. So the voltage gain can be higher than 1 or lower than 1, just like the other converter, like a buck boost converter. Okay, but of course there are some differences. What's the difference? What's the difference? We also can understand from the origin of the converter, because we have the current source here on the source part. We also have the current source on the load part. So we can expect the input current source is limited. Okay, and so as load current. So for the input and output, their current ripples are very limited. because of the inductor or the current source properties. And we can also expect the input voltage ripple and output voltage ripple are also limited. Okay. And remember, for the buck boost converter, both the input and output current ripple and the voltage ripple are not satisfied. Okay. Okay, so we have the new converter here, and here I just read the text here. The true converter is similar to the buck boost converter. The polarity of the input and output voltage is reversed. That is, the input voltage polarity is positive at the top and negative at the bottom, while the load side is reversed. Okay, just like a buck boost converter. And yes, the voltage level can be higher and lower for the output side. And the capacitor C1 is a buffer to transfer the energy to the output, because we cannot directly transfer the power from the current source to another current source. So we have the current source to voltage source and then back to the current source. Okay, so C1 is a buffer to transfer the energy to the output, and in steady state, the average inductor current are 0. We already know that, right? Under steady state, the inductor average voltage will be 0. Okay, and now we want to use this property. Please focus on this loop. Okay, we have this loop. For this loop, if we write the KVL equation, what's that? We have a minus input voltage plus the inductor voltage L1 and capacitor voltage VC1 and minus VL2 and minus VO. This will be 0. You know that from the KVL equation. And if we take the average of all the variables, okay, then we know the average of VL1 and VL2 are both 0. Okay, so we have the VC1, the average voltage VC1 will be equal to the input voltage and output voltage, the sum of them. Okay, so we have the conclusion here. The capacitor voltage is the sum of the input and output voltage. Of course, the polarity of VC1 will be positive on the left side and negative on the right side, because the input voltage polarity is like this and output voltage polarity is like this. Okay, then we can understand the operation of this converter. If the switch, the switch and the active switch T is turned on, okay, if T is turned on, we have a loop here, right? And also, you know that the diode is reverse biased. Okay, the diode is reverse biased because of the polarity of the capacitor voltage. Okay, so for the load part, the inductor current will pass through the capacitor and through the active switch back to the load. We have two loops. The first loop is like this, and the other loop is like this. When the switch is turned on, and when the switch is turned off, okay, when the switch is turned off, then the inductor current IL1 will pass through the capacitor and force the diode to turn on. So we have this loop. and also the inductor current IL2 will pass through the diode. Okay. When switch is on and off, we have two different operation modes. And we also know that we can know the inductor voltage. For VL1, when the switch is turned on, the voltage will be equal to the input voltage. And the VL2 will be equal to, it's a little difficult for me, so I will use the KVL to find the VL2. When T is turned on, then we have VC1 and minus VL2 and minus VO. It will be 0. Okay, so we have a VL2 equals to VO minus VC1. Okay, this is when switch is turned on. And then when switch is turned off. When switch is turned off, okay, we have a loop here. So the VL1 will be equal to the input voltage minus VC1. Okay. And VL2 will be equal to negative V1, negative VO. Okay, you know why we want to know the inductor voltage for every mode. You know why? Because we want to use the volt-second conservation to find the voltage gain. Okay, so we have the equivalent circuit like this, and we have the voltage like that, and then we use the volt-second conservation. Then we can find out the voltage gain is like this. And the voltage gain equation is exactly the same as the buck-boost converter. Okay, this is the first approach, and we have another approach to find the voltage gain. The other approach is to make use of the charge conservation of the capacitor. Okay. The charge conservation of the capacitor, because for the capacitor C1, we know under steady state, the average current of the capacitor will be 0. So the current injected into the capacitor will be equal to the charge out of the capacitor. Okay, so we have to know that when the switch is turned on, what is the capacitor current? Okay, when the switch is turned on, what is the capacitor current? You know, the capacitor current will be equal to the IL2, right? But it's negative IL2 because the current flows through the negative terminal to the positive terminal. So the current is negative. Okay, and when the switch is off, then IL1 will pass through C1. So the current will be IL1 and it's positive. Okay, so for the second approach, we have when the switch is turned off, the charge into the capacitor will be IL1 times, this is the period, this is the interval, the current into the capacitor, because switch is off. Okay, and when switch is on, it's IL2, and the interval is DTS, and they should be identical. Okay, when they are identical, we have the IL2 over IL1 will be 1 minus D over D, and because IL2 actually is output current, and IL1 is the input current. So this ratio is also the current gain. And if we assume the efficiency is 100%, then the inverse of the current gain will be the voltage gain. Okay, so we have the voltage gain like this. Of course, they are the same. Okay, and yes, we have some assumption here when we derive the equations. The assumption here is the voltage ripple of C1 is ignored. Okay, the voltage ripple of C1 is ignored for the first approach, and for the second approach, the current ripple are ignored. But that's okay. Okay, so for the Chuk converter, there are some properties, and the first is the ripples on the both sides will be small, and the voltage ripples are also small. Okay, this is the most important advantage of the Chuk converter, and compared to buck boost, the current ripples are large, and the output the voltage ripples are also very large. However, there is some disadvantage. Of course, the first disadvantage is there are more components. We need an extra inductor and an extra capacitor. Okay, this is the first disadvantage. And the second is the current ripple through the capacitor C1 is high. Because when switch is on, here, when switch is on, all the IL2 through C1, and when switch is off, all the IL1 through C1. Remember that? When we discuss the output capacitor, okay, when we do the analysis of the output capacitor, only current ripple, only the AC components flow through the output capacitor, right? But here, all the current will through the capacitor. Because now we have to use this capacitor as the energy buffer to transfer energy to the output. So all the energy have to pass through the capacitor. Okay, so the ripple current is high on this capacitor, and also the service life of the capacitor is limited because of the high current ripple. Okay, so basically for this converter, the reliability is lower than the other converters because of the capacitor. And if we want to use the capacitor to store a large amount of energy, then we have to choose the right capacitors. Usually here we have to choose the electrolytic capacitor, and unfortunately, that kind of capacitor has the lowest life. Okay, so although there are some advantages, this converter is not so popular. Okay, and we have another kind of similar converter. And this converter is called SEPIC. The full name is single-ended primary inductor converter. Basically, I don't know what does it mean of the full name. Basically, I don't know, but everybody called it SEPIC converter. And basically, the converter have the same components like the Chuk converter, but the arrangement is different. You can see if we interchange the inductor and the diode, then we have the Chuk converter. Okay, so we may expect that this converter will have a similar have similar properties like a chip converter. Okay. When we analyze the converter, okay, we find a loop. We just find a loop to find out what is the average capacitor voltage. Okay, we can find this loop. From this loop, under steady state, what is the average capacitor voltage? We already have one experience earlier, right? So if we apply the same theory here, what is the average capacitor VC1? VE, right? Yes, VD, yeah, the input voltage. Okay, so we know of course there will be difference. The first difference is the capacitor voltage is lower. For the tube converter, the capacitor voltage is the sum of input and output voltage. But here, the voltage is only equal to the input voltage. Okay, the capacitor voltage is lower. Okay, and you can find that the output voltage polarity is also different. For the choke, it is upside down. It is negative at the top and positive at the bottom. But here, the voltage polarity is the same as the input voltage. Okay? But you also can expect that only from the topology, you already know that the input current and voltage ripple is smaller. But the output current and output voltage ripple will be higher. Okay, and then we can also find out what's the operation mode of the converter when switch is on and switch is off. Here, when switch is on, we have the loop here. Okay, and when switch is on, how about the diode? How about the diode? Will the diode be forward biased or reverse biased? Sure, we will guess the reverse biased. But the reason, you also have to know the reason, right? And the reason usually is very apparent because the voltage across the diode will be the sum of the VC1 and the VO. So of course it is reverse biased. Okay, and when the switch is off, of course the inductor current will pass through the capacitor and through the diode. And so when the switch is off, then the diode should be forward biased. And we have two current. Okay, one current here and the other current here. Okay, so you can also find the equivalent circuit like this, and from the equivalent circuit, you can find the inductor voltage for the two inductors, and then you can again use the volt-second conservation to find the voltage gain. And the voltage gain is the same. It is also like a buck boost. Okay, And then there is a question. There is a question. Why we have to use this kind of converter? Okay. Why we have to use this one? Now we already have the Chuk converter, and for the Chuk converter, both the input-output current voltage ripples are very small. But for this one, the output ripple actually is not so satisfying. So why we use this one? Uh, this is the example. Okay, this is the example. This example is power factor correction. Okay, this is a power factor correction because you know this is AC line in, AC AC voltage here, and we have the a rectifier. Also, this is AC to DC, and the AC to DC connected to this part. Usually, for the power factor correction, we usually use a boost converter. Okay, we usually use boost converter because there is an inductor connected with the input source. So the input current ripple will be small. That is what we want for the power factor correction. So we have the configuration like this. Okay, and we can also replace this inductor with a transformer. Okay, this inductor is very easily to be replaced by a transformer, and if we have this transformer, then this will be an isolated power factor correction circuit. For the boost converter, it is not isolated. But for this one, this is isolated. So if we use this static converter, we can use for the PFC, the power factor correction, but it has also the isolation capability. So usually when we talk about the SEPI converter, usually it is used for the power factor correction. Okay. Then maybe you can try to compare the SEPIC and the Chuk converters, and also I can remind you that can you try to synthesize with two basic converters to obtain this SEPIC converter? We have three basic converters: the boost, the buck, and the buck boost. We have these three basic converters, and if we synthesize two of them, then we can generate a new converter, right? And we already have we have tried. If we synthesize buck and boost, or boost and buck, then we already have two different converters. So, can we try to synthesize a boost with a buck boost, or a buck with a buck boost? Okay, you can try. Then you can generate a new converter by yourself. Okay, so try. How can we get this converter via the synthesization process? Okay. Then I want to talk about the isolated converters. And because the isolated converters, they are the main feature is there is a transformer. So now I want to talk about the transformer. Okay. Of course, I think all of you are familiar with transformers. But now I want to talk about practical transformer, not ideal transformer. Right? You already know what is ideal transformer. Okay, we can talk about it. for ideal transformer, you know, the voltage gain, the input voltage, not the input voltage, I will say the primary side voltage, okay? The primary side voltage versus the secondary side voltage, that is turn ratio, right? And also you can know that the primary side current over the secondary side current will be the inverse of the turn ratio, right? For ideal transformer, this relationship is always valid, right? But may I ask you, if there is no current, through the transformer windings, for example, if there is no current through the secondary winding, then what is the current of the primary winding? Not exactly. You mean when the secondary side current is zero, but the primary side is not necessarily zero? By what? Oh, oh, okay. You are right, but I'm talking about here. I'm just talking about ideal transformer. Yeah. Okay. So we have the concept of ideal transformer, but of course a practical transformer is not ideal. Okay. So we have the for a transformer. Of course, we need a iron core. Okay, we need an iron core, or sometimes we will say it is a magnetic core. And usually the core is made of iron. Okay, made of iron and some other elements. Okay, and of course for a transformer, there should be at least two windings, and sometimes we have three winding, four winding, okay, but at least there will be two winding. Okay. And for the windings, the windings are composed of copper wires. Okay, they are copper wires, and you know, for the copper wire, the resistance is not zero. So you always for each winding there is a resistance. Maybe we can say this is ESR, the equivalent series resistance. Anyway, there is a resistance for the winding, and you also know that if a current through a winding, okay, if the current flows through winding, there will be the magnetic flux. Okay, there will be the magnetic flux, and most of the flux will be confined inside the magnetic core. Okay, most of the flux will be confined in the region of the magnetic core. But there is some leakage flux. Okay, there is some leakage flux will flow out of the core. Okay, so we have the leakage flux. And also for the secondary winding, the same thing happened. If the current through the secondary winding, there is also the flux will be generated. And there is also the leakage flux. And you also know that the flux generated from the primary winding will be cancelled by the flux generated by the secondary winding. Okay. The flux generated by the two windings actually they will try to cancel each other. So if this is an ideal transformer, maybe I have to say, if the iron core is perfect, Okay, if the iron core is perfect, then the flux generated from the primary side will be completely cancelled by the flux generated from the secondary side. Then there is no flux inside the core at all. If the core is perfect, okay. When we say the core is perfect, what do we mean? Usually we mean that the permeability of the iron core approaches to infinity. Okay, if the core is perfect, then the permeability will be infinite. Or we can say the reluctance is zero. Okay. But of course, no iron core is perfect. So there is still some flux inside the magnetic core. That is, not all the flux from the primary side is cancelled by the secondary side. So there is a flux inside. That is to say, for the primary side, it have to supply the current first to cancel the flux from the secondary side, and second to provide the flux inside the magnetic core. Okay, for the secondary part, that is like you say, the magnetizing current. Okay, so the primary side have to supply we can say, to supply the load current and also supply the magnetizing current. Okay, so if when we want to generate the equivalent circuit of the practical transformer, then we have first we have the ideal transformer here. But in addition to that, we have the leakage inductance and the resistance, both on the two windings. And for the primary winding, there is also a magnetizing inductance. Okay. So this inductance is to provide the magnetizing current. Okay, so this is a more complete equivalent circuit or model of the practical transformer. Of course, you can have a even more detailed model for the transformer. Okay, actually there is a capacitance. There is capacitance between the windings. So there is also the parasitic capacitance inside the transformer model. But here we don't discuss that because all that capacitance only the effect of the capacitance will be apparent only under very high frequency. Okay, so in the power applications, we neglect the capacitance here. We only have the magnetizing inductance and the leakage inductance. Of course, the resistance. You can find the parameters of this model by the LCR meter. Okay, you can use the LCR meter to find these components, these parameters. Of course, it needs some knowledge about how to find the parameters, such as you have to use a short circuit test or open circuit test to find the parameters. Okay, but we don't discuss it here. And here, for the practical transformer, especially in the lab, we have to build the transformer by ourselves. Okay, And in the lab, you will usually use a core like this. And this core usually are called EE core or EI core. They are EE or EI core. That is, the core itself is okay. There is an E-type. There is E-type core, and if you have another E-type core, then you just put them together. You have the here. Okay, if you have two EE core, then you can put them together. Then you have the shape like this, or you have a E core and another bar. The bar is I. Right? You can also form the shape like this. You use an EE core or EI core, and if we use the EE or EI core, then we have to use bobbin. Bobbin. I don't really remember. Maybe like this. We have to use a bobbin. Bobbin is like a plastic, skeleton. Then we can wind the windings on the bobbin. Then we can just put the core into the bobbin. Then we have the transformer like this. Okay. And here we have two windings. You know, if I assume that the current flowing through the left winding from the terminal A, and if I assume that the voltage polarity is like this, the positive on the top and the negative at the bottom. Okay, then we use the right hand rule. Okay, we can determine the flux direction by the right hand rule. For the the winding AB, then we have the flux upward, right? And for the secondary winding, you know the flux direction will be downward because you want to cancel the flux from the primary winding. Okay, if the flux is downward for the secondary winding, then the current direction will be like this, right? The current flow out from terminal C and into the winding from terminal D. Right? And if we connect a load at this terminal, if I connect the load, then you know the voltage polarity will be positive here and negative here because there is a current out of terminal C. Is it correct? Okay. If that is correct, okay, then we can conclude that how we mark the dot of the winding. Uh, if the for the primary winding, the dot terminal is positive polarity, then for the secondary winding, the dot voltage polarity is also positive. But for the current, if the current flow into the primary winding from the dot terminal, then for the secondary winding, the current will out of the dot terminal. Okay. For the voltage polarity, both sides at the dot position, the polarity is the same, but the current flow into the dot. Then for the other side, the current will be out of the dot. we have to use a dot. We have to use a dot to mark the terminal of the winding, because you cannot always sketch. You cannot always sketch or draw the transformer like this. Usually we use this symbol, right? And if we use this symbol, we have to use a dot to identify the priority of the windings. We cannot know the current flow and use the right hand rule to determine the priority, right? Okay. And here, the magnetizing inductance usually for a transformer, it is very large. Usually it is very large, and we hope the magnetizing inductance is as large as possible to be a perfect transformer. Okay, so we hope the permeability to be as large as possible, then the reluctance will be very small. Okay, but for a transformer, you always have to understand there is a magnetizing inductance. So for the later discussion, we will make use of the magnetizing inductance. And before that, we just review some of the variable definitions and the equations or laws. The H here is a magnetic field intensity, and the B is a flux density, and the lambda is a flux linkage, and the phi is a magnetic flux. This is Chern's number, and L is a magnetic path length. I will not go to detail of the definitions. Also, we have the Gauss's law for the magnetic fields here, and I'm sure you're familiar with the Faraday's law. Okay, the Faraday's law here, the differentiation of the flux linkage will be equal to the voltage, the induced voltage. Okay, and the negative sign here is the Lenz law. Okay, so usually I think this is not so important. You just remember the differentiation of flux linkage, or the differentiation of the flux times the Chern number. Then we have the induced voltage. Okay, I'm sure you're familiar with this. And we also have the Ampere's law. For the Ampere's law, we have the magnetic field intensity is times the path length. Then we have the Ni. Okay, and I have to add some more relationship. Why cannot change? We also have the flux will be equal to the permeability times the magnetic field intensity. Okay, and so we have the B, the flux density will be equal to mu times L and no. The B also equals to the permeability times L and I, right? And then we can say, because phi actually is equals to the flux density times the area, the core area, the cross-sectional area. Then the phi will be mu times L, N, A, and I. Okay, so what I want to say is phi actually is proportional to the current. But you also have to know that because the mu or the permeability actually is not a constant. Okay, here we have the relationship here. The B equals to mu times H. But the relationship between B and H, they are not linear. They are not linear relationship. So the mu actually is not a constant. When the H is higher than the flux density, generated flux density is lower. Okay, you know this is called saturation. Okay, so for the design or the manufacture of the inductor or transformers, you always have to remember, we have to avoid saturation. Okay, we always have to avoid saturation. You always have to remember that. Okay, so although the flux is proportional to the winding current, but the relationship is not linear. Okay, and sure, basically, if the current is higher, then the flux is larger. Okay, basically, it's like that. But that is not linear. For the two windings, they are they are wounded in a same magnetic core. We can also use the concept of the mutual inductance to explain the relationship here. Uh, in this page, actually it is to derive that the conclusion is that the M21 is equal to M12. That is, if you find the mutual inductance from this side of the winding or from the other side of the winding, the inductance are the same. The mutual inductance are the same. Okay. So for the mutual inductance, for the analysis, you know, basically the voltage equals to the L1. L1 usually we say this is self-inductance. Okay, the self-inductance times the current differentiation and plus the mutual inductance and the current differentiation of the other side of the current. Okay, we also have the V2 like this, and if we use a phasor analysis, okay, we transfer the equation into the phasor domain, then we have the equation like this. Okay, I'm also sure you're familiar with this. Both the approaches, if you use a mutual inductance to analyze the circuit, or you use a equivalent circuit model like this, basically we have the same result. Okay, basically we have the same result, and we can actually we can prove that the two approaches we will have the same result. Okay, but for me, I prefer to use this model to explain the relationship between two windings. For me, of course, you can use another approach, but I prefer this one. Okay. Okay, so we start our first isolated converter. The converter is called flyback converter. This is the Chinese. In the Chinese, it is basically the meaning is not so clear in the Chinese, but also from the English name, the meaning is not so clear. Okay, but we can say why we say this is a flyback converter. That is the energy. The energy basically is stored in the transformer first, and then sent to the other side. It is not directly. The energy is not directly from this side to that side, but it is first stored inside the transformer and then sent to the other side. Okay. I think we can take a break first. Break first, not break first.
你打点方向错了吧？
真的吗？
对啊，因为如果上面那边是开电的话，那下面应该是打点在下面。
看一下。
那磁通是向上啊。
嗯。
那磁通如果上面是上正下负的话，它应该是这样子，所以打点在这边。啊，磁通是这样向上，所以它打点应该是在下面。电压是在下面出来啊，所以电流是 C 端向内。
它上面是这样子上去，对不对？那下面要这样子吗？
可是总磁通不是一次侧产生的吗？
是一次侧产生的，但是二次侧磁通的电流方向是要产生一个反向的磁通啊。
是电压吧？
磁通是要反向。你一次侧产生这一个方向的磁通的时候，二次侧的电流一定要产生一个去抵抗它的磁通。
那个不是楞次嘛，所以它
是啊，是楞次啊。
对啊，那电压是下正上负的话，那电流如果后面是挂那个电池，那电流应该是从 C 端进去，D 端出来嘛。
它必须是这样子的磁通。你一次侧是往上的磁通，二次侧就要往下。你不可能两侧的磁通是相加的啦。
可是它不是在同一支上面吗？
同一支上面也一样啊。你如果不要用同一支的话，你这样看啊。如果这样看，我右边它都是在过来，然后二次侧是要往下去调的。这样对他来讲，他接收的话，他这样下来是从下。对啊，他遇到一个这样的情况，结果要去调它。